and participating today in this SISSA IFPU seminar, and Claudia to be here. So today we have with us Claudia de Rham. Claudia is currently faculty chair at the Imperial College in London. Claudia has a vast experience on the study of the meeting point between gravity, cosmology, and particle physics, as seen in the numerous citations and articles published in the prestigious scientific journals. Through her academic year, she has been dedicated to the study of different topics. For instance, massive gravity, scalar tensor theories, UV completion of gravitational theories. Claudia got her PhD from Cambridge University, and afterwards she moved to Canada as a postdoctoral research in McGill University and Perimeter Institute and McMaster. She has been professor in Geneva University, Case Western Reserve University in Ohio, and now she's a member of the theoretical physics group at Imperial College in London. Today, she will talk about causality in curved space. So go ahead, Claudia, and thanks to here.
Thank you very much. Thank you for the invitation. I apologize I couldn't come to Trieste. It would have been nice to meet you all in person, but hopefully the remote talk will do instead. And I also like to thank my collaborators who's done all the amazing work in here. So anything you enjoy about this talk is thanks to these amazing collaborators. And all the rest you disagree with, that's of course all my fault. So what I'll be talking about today is within the context of the low energy effective field theory that includes gravity. So I'll have gravity at the center of most of what I'll be talking about today, but it's not necessary that I'm going to be looking at processes that are just gravitational processes. A lot of the questions I'll be asking or can be asked are related to other species that just happen to be living in effective field theory that also includes gravity. And the fact that it interacts with gravity has some effect on this low energy effective field theory and on these species. The questions I would like to answer or to tackle is related to, in some aspect, gravitational waves and whether or not they could be superluminal, and also other species, for instance, light or other species you may be interested in, for instance, the inflaton or the dark energy field, whether it makes sense or not for those to be considered to be superluminal. And I'll try to understand the connection between those mild level of superluminality and the notion of causality, and whether low energy effective field theories that could have a very mild amount of superluminality could possibly be embedded within a standard UV completion, or whether we should draw the line at that level. So before I go into the core of what I'll be talking about and the connection between superluminality, causality, and standard UV completion, let me just review some of the results that you all know, and some people in the audience are, of course, much more expert on that than I am, particularly related to the current bounds that we have on the speed of propagation of gravitational waves. So we know since the event of the summer 2017 that the gravitational waves travel at the same speed as light within an incredible accuracy, 1 part in 10 to the 15 or 10 to the 16. The frequency of light that has been observed is extremely high. So for all intents and purposes, the speed of light at those frequencies is 1 to an even much better accuracy, even if we accounted for any small corrections that took arise for the speed of propagation of light at those frequencies. And so this bound that we have from the summer 2017 can really be understood as a bound on the speed of propagation of gravitational waves at frequencies related to that of LIGO. Now, a lot of models of dark energy would predict a non-luminal sound speed for gravitational waves due to the interaction between gravitational waves and dark energy, and following the direct detection of gravitational waves with optical counterpart, a lot of models of dark energy that would otherwise have predicted a non-luminal sound speed for gravitational waves can be ruled out. So this is really just a cartoon picture. Don't take that too seriously. There's some caveat associated with many models of dark energy, so it's not as clear-cut as that. But if I was to try to describe various models of dark energy that have been proposed in the past 10 to 15 years in the literature, we can put a bound, or we can rule out now many models of dark energy based on the fact that those models will lead to a speed of gravitational waves propagation which departs from 1 by more than 1 in 10 to the 15, minus 10 to the 15. And this was explained extremely well by some people even present in the current audience. Now, a potential caveat, which is not so relevant for what I'm going to be talking about today, but good to keep in mind, is that many models of dark energy that are presented in this cartoon picture are actually low energy effective field theory, which have a region of validity which is actually pretty low and are really built in so as to be appropriate descriptions of what's going on cosmological scales for dark energy. So have a very low region of validity and are really more intrinsic to this region in energy scale. And so it is possible to consider some models where the speed of gravitational waves could still depart from that of light at very low frequencies and would then naturally go back to luminality. We would expect any models that lead to departure of the speed of gravitational waves at low energy, if this departure is simply due to interactions with dark energy, for instance, on a background that spontaneously breaks Lorentz invariance, we would naturally expect from the restoring of Lorentz invariance at high energy, the speed of gravitational waves to go back to 1, being exactly 1 at high energy. So without too much tuning, one could expect to have some models that could survive, leading some departure of the speed of gravitational waves at low energy while being mildly consistent with observation at LIGO scales. So this is not too important for what I'm going to be talking about because the orders of magnitude I'll be talking about are ridiculously small compared to those ones, but it's just to set up the framework in which I'm going to be working. One question I like to ask is whether this current bound is even being too generous, and we should even constrain the speed of gravitational waves to not be superluminal at all. Should the option that the speed of gravitational wave could be mildly larger than 1 could even be considered as a possibility, or should we set as a prior that the speed of gravitational wave has to be strictly luminal or subluminal? And this type of consideration is often imposed as a prior in comparing data with models or effective field theory for dark energy. So we like to understand whether this should be put as a prior or whether this type of constraints should still be allowed in the framework we're considering. So I'll start by understanding what happens for non-gravitational theories, because this is the type of prior we would expect for non-gravitational theories, and see what happens or what can be different when we include gravity in the game. So if I consider a non-gravitational effective field theory, one can show that there's a direct connection between having a UV completion for our theory, which is a standard one and in which causality plays a crucial role. There's a direct connection between having a consistent causal high energy completion for our low energy effective field theory and our low energy effective field theory having strictly luminal or subluminal speed of every species present in our non-gravitational effective field theory. And this can be explained more precisely through the use of positivity bounds. I'm going to summarize very quickly what we mean by positivity bounds, but I'll just like to remind you that there's been a beautiful talk from about 2 months ago, working out through the positivity bounds in the non-gravitational and then in the gravitational setup. So I'm not going to make justice to everything that has been explained in that talk, and I will refer you to that for any questions you may have. But the framework from the positivity bounds, which allows you to make a connection between causality and standard UV completion and that of subluminality of every species at low energy, is considering a 2-2 scattering amplitude within our low energy effective field theory. So whatever your low energy effective field theory is, whatever field lives at low energy, it can be the dark energy field, if, for instance, or anything else you may be interested in, but for now, without gravity, I can consider an elastic scattering amplitude. I'll be working in Mandelstrom variables, so S is my center of mass energy squared, T is my momentum transfer. And if I require that this low energy effective field theory enjoys a causal UV completion, the notion of causality is embedded in this context within the notion of analyticity, which I'm not going to have time to make the connection concrete in here. You just have to take my words for that, which means that the Scattering amplitude can be extended in the complex S-plane, and it has to be analytic in the complex S-plane aside from some poles or some branch cuts in the real axis. Then the notion of locality tells us that the amplitude has to fall fast enough at infinity in such a way that the amplitude over S cube has to go to 0 at infinity. And so I can compute this integral, and this integral will be finite from locality. The notion of analyticity here, I haven't said it, but I'm using in performing a Cauchy integral so that I can relate anything that happens in the real axis to something that happens at very low energy, so that I'm interested in scattering amplitudes within the low energy effective field theory, possibly even at S is equal to 0. Then the requirement that my UV completion be Lorentz invariant, even if I'm considering my low energy effective field theory living in a background that may be breaking spontaneously Lorentz invariant, we have in mind the idea that at high energy, Lorentz invariance would be restored because the breaking of Lorentz invariance at low energy is only spontaneous due to the presence of matter, for instance. The notion of Lorentz invariance is then for us related to that of crossing symmetry, and I can relate what's happening within some branch cut in the positive part of the real axis to the branch cut in the negative part of the real axis with some different channels of the amplitude. You don't need to worry about that too much. And then one of the most crucial ingredients is that of unitarity, which manifests itself through the optical theorem that tells us that really the cross-section, or in here, the imaginary part of the amplitude has to be positive. And so the positivity of the imaginary part of the amplitude on the real axis, which is here, can be continued analytically through the notion of causality at S is equal to 0 and lead to a statement about the amplitude at S is equal to 0 or small s, and more particularly about the second derivative of the amplitude at small s. And this manifests itself in the requirement that the second derivative of the amplitude at S is at S small and at t is equal to 0 has to be positive. This has to happen for any effective field theory at low energy if it has to enjoy at very high energy a completion which is causal, local, Lorentz invariance, and unitary. And we can relate this statement about the positivity bounds then directly within a low energy effective field theory to that of subluminality of the sound speed. And the very notion of causality is anchored within those positivity bounds and anchored as we know them within the notion of subluminality of the sound speed. So often we take shortcut and we just have in mind the notion of causality being directly related to that of subluminality, but in reality it goes much more through the notion of positivity bounds to be able at low energy to impose the notion of subluminality. Okay, so this is for non-gravitational effective field theories. Now what we would like to do is add gravity in the game. And both the requirement of subluminality and positivity bounds are much more subtle for any gravitational effective field theory. Even for an effective field theory in which what you may be interested in is not necessarily gravity per se, even if you're interested just in the speed of propagation of dark energy or any other field in the Stoner model, if this effective field theory is intrinsically embedded within a gravitational framework, the very interaction with gravity will lead to some requirement about the positivity bounds or some requirements about the speed of propagation, or sound speed, energy, which may be different as compared to what would have happened had gravity not been. So in order to understand why this is more subtle in the gravitational setup, it's actually easier to go back to the positivity bounds. And if we look at any process that happens within a low energy effective field theory that includes gravity, there would be, or there can be in principle, even if what you're interested in is just the scattering of electrons, for instance, there would be, as soon as you include gravity in the game, some processes that allow for a gravitational exchange. So this is my poor attempt of depicting this gravitational exchange. And that will lead to a new contribution in the amplitude, which is related to what we call a T-channel pole. It goes like 1/T related to the fact that the graviton is massless, and it grows like S squared. And this S squared behavior is really related to the fact that the graviton is a spin 2 particle, and so it will grow like S squared. So this is very intrinsic to gravity. If you just looked at an interaction with another massless particle of lower spin, for instance, a photon, the amplitude will go like, you still have a T-channel pole, but the amplitude will go like S itself and wouldn't be present in the second derivative of the amplitude, the real part of it. And of course, this is also related to the fact that gravity is a massless, the graviton is a massless particle. And so you really have just a T-channel pole here. If you wanted to, you can resolve all of this by making gravity massive. And then you would have a massive pole here, which would be finite as T is equal to 0. So really the issue is with the presence of a massless particle that has spin 2 or higher, as is the case in any gravitational theory or in any theory that has higher spin, massless higher spin. And the very presence of this T-channel pole means that the amplitude is not analytic at T0, and we can't be removed from this second derivative, and so compromises the applicability of those positivity bounds in a gravitational effective field theory. So with that in mind, the best thing one can do is simply to say that if I'm able to take a scaling limit where I send the Planck scale to infinity in such a way that other quantities remain finite in my low energy effective field theory, then the presence of the T-channel pole will disappear and the Planck scale goes to infinity limit as gravity decouple. And then I can go back to a situation where the interaction with gravity is irrelevant, and I can just put my positivity bounds on the remainder of the contributions to the amplitude. So put that a little bit more concretely, and the precise scaling may not be obvious in here. Hopefully it'll become a little bit more obvious later on. But the bottom line is that if an amplitude, a scattering amplitude in the presence of a gravitational T-channel pole scales like that, in the Planck scale goes to infinity limit, in the strict Planck scale goes to infinity limit, this can be used to put a bound on this coefficient. This is just the coefficient I'm using to parameterize the amplitude being positive. That's what the positivity bound will tell me as m Planck goes to infinity when the scale m or the scales in the system remain finite. But we can be a little bit more precise about this. When m Planck is finite, the quantity P itself does not need to be strictly positive, but rather has to scale with something that may be slightly negative, but in such a way that will go to 0 as m Planck goes to infinity. Okay, this precise scaling, the fact that it's m squared of m Planck squared may not be completely obvious to you, but hopefully it's obvious that this has to scale like negative powers of m Planck. So now, with this notion of approximate positivity bounds in a gravitational effective field theory, we can go back to what we mean by the notion of causality when it comes to understanding the speed of sound. So just to summarize, really the context in which we're working here, in a standard non-gravitational effective field theory, standard positivity bounds tell us that the coefficients in the amplitude have to be positive, the ones going like s squared, and this is very much related, for reasons I'm not showing you explicitly, but just take my word on this, this is very much related to contribution that will lead to departures of the speed of light, or the speed of sound speed of the species you're considering. And so requiring this coefficient to be positive is analogous to requiring that the sound speed of the species living in the low energy effective field theory have to be subluminal. Now, as soon as you introduce gravity in the game, whether you're interested in scattering that include directly gravity as external legs or not, even if you're interested in other processes, the scattering amplitude does not need to satisfy quite the same positivity bounds. It's more of an approximate positivity bound, where the coefficient here could have a mild level of negativity. And so what we'd like to understand is what the implication for the sound speed of propagation, or the sound speed of any species living in a low energy effective field theory when you include the gravitational context. So I'm going to go through various examples, and I'll try to build in a framework where we can try to understand that a mild level of superluminality at low energy may be acceptable and not necessarily directly related to causality violation, so long as it scales in a way which is going to be similar to what I'm imposing in here.
Claudia, can I ask a question?
Yes, yes, of course.
Yeah, it's Marco here, sir. Hi. So there is something I don't understand. So whenever you include gravity, so you are still relying on all the set of causality, analyticity relation that we like and love, which are strictly speaking only established rigorously in the case of non-gravitational theories. So I was wondering whether we can buy that and and maybe there are some little non-analyticity that one can suppressed by 1 over m Planck, for instance, that one can imagine that will then tell you that there are yet other contribution to the amplitude coming from some non-analyticity due to induced by gravity, which don't appear in your formula here.
So the analyticity, the connection between analyticity and causality, this is not really, we don't expect this to be really modified by gravity. The presence of gravity shouldn't affect that. This notion of causality, a connection with analyticity, is really requiring the absence of support outside the light cone at sufficiently large, well, everywhere. So it's just the ability for us to being able to perform a Cauchy integration, close the contour, and not having any support within the complex plane that would lead to some presence in the retarded propagator. So this particular aspect, I don't think we should give up. What happens? Yes.
Yeah. Sorry. The causality is simply the micro causality on the light cone. On light cone is defined on the light cone, which is the flat space light cone. This is the analyticity which we used to base all the analysis in the non-gravitational case, right? So in presence of gravity, the micro-causality condition becomes more subtle because which light cone you should use is not totally clear. It's no longer the flat space one. So in this sense, there might be modification to the analysis. I mean, I'm not saying that they do not apply. I'm saying that it's not totally clear to me that this set of things that you write here, the causality, locality, Lorentz invariance, unitarity, straightforwardly apply in the gravitational case. Yes.
No, so you can absolutely question those requirements, and one should, of course, but I think that of locality is probably the one that should be questioned the most. So definitely the Froissart bound is
also,
requiring the amplitude to not to grow faster than s squared. And actually at low energy, of course, in the gravitational setup, it will grow like s squared. However, when the reason we kind of try to use it still here, even though it's not being proven that this should be satisfied for a gravitational theory, is because we think that as you go to high energy and you go within the string theory setup, it will go back to satisfying the Froissart bound. So you will have some violation of locality in the completion of in the completion of gravity, but by in a way that manifests itself so that we would expect the Froissart bound to still be satisfied. However, there's no there's no strict proof of that, of course. I mean, there's definitely room for questioning those assumptions, but I think that of locality is probably the weakest one as compared to that of causality. I mean, the notion of analyticity I'm using, if you start breaking that, then yes, I'm anchoring this to that of causality. So and then I'm giving up even more than I'm willing to. So I'm really trying to be conservative here. I guess what you want to say is maybe this notion of analyticity should be even broken further, so that ultimately at low energy, the bounds that we're gonna work out could be broken even further. So I'm just gonna remain quite conservative.
Okay.
But I guess even if you are happy violating some of those bounds, ultimately one should still have a bound of this form. Maybe we can disagree on the precise scaling, but even if you want to violate this notion of analyticity a little bit more in the gravitational setup, or even more in the notion of locality in the gravitational setup, all we can dispute about is the precise power here, right? Would you agree with this?
Oh yes, yes. I mean, I've been focusing on causality, but I must say that a similar comment can applies also for crossing. Now, crossing also, which is a crucial property in the. I mean, I'm not aware of any say way to understand how crossing can be extended in the gravitational case. I mean, aside from string theory, I mean, I agree with you that in string theory it's built in, and with specific UV completion, I understand what you have in mind. Certainly, I agree. But from this generic context, how crossing, why crossing is satisfied in gravitational sector is non.
No, it's not trivial. I agree.
It's not
I agree.
clear. So anyhow, okay,
but bear in mind that I mean, I'm still considering some restoring of I mean, it's still Minkowski at sufficiently high energy, right? Everything, all the, I mean, a lot of the point you raise related to a potential breaking of crossing symmetry or some subtleties on how it manifests themselves. This is more just to do with the geometry, not being Minkowski, right?
yes.
Yeah, but at sufficiently high energy, I have in mind everything will go back to Minkowski, exactly Minkowski. So that is definitely the framework in which I'm thinking about it.
Okay.
Yeah.
Thanks.
Okay. Okay. So before I go into directly relating this notion of, hopefully we agree, we can approximately break the positivity bounds in a gravitational setup to that of the sound speed within my low-energy effective field theory, I'm just going to spend a few slides discussing about some trivial but yet important caveat related to frame transformations, and just so that we set up the context in which we'll be working about and we don't need to worry about this anymore. So let me consider an effective field theory for a scalar field without gravity to start up with. So this is my low energy effective field theory in the Wilsonian sense. I'm integrating out my heavy modes, and let's just as an example think that I have a light field phi. It can be massive, but just too lazy to introduce its mass, and I have a heavy mode which interacts with phi, and then I'm integrating this heavy field H. I'm working at an energy scale below the mass of this heavy field, and this interaction between the heavy field and my light field manifests itself now in my low energy effective field theory through this contact term. Now, the unitarity and some level of having some well-defined semi-UV completion in here tells me that this coefficient here has to be real, and that manifests itself in this coefficient here being real, and it manifests itself in the speed of sound of the scalar field phi within my low energy effective field theory being always subluminal. So to see any departure from the sound speed at low energy, we need, of course, to start breaking spontaneously Lorentz invariant in the first place. So if you consider a background which is Lorentz symmetric, you're just going to have a speed which is 1. But if you're considering a cosmological setup or a black hole or whatever you want that spontaneously break Lorentz invariance, you can start having some departure in the speed of propagation, on the sound speed of the fluctuation of the field about that background. And the fact that they are subluminal is related to the fact that this coefficient here is always positive, no matter what type of configuration you're considering. Okay, so this is the connection loosely, in a loose sense, of what I was discussing about. So in the absence of gravity, I can consider this low energy effective field theory, and I have that the sign of this coefficient here being positive is related to the fact that the light cone for my fluctuations about any background that I want are going to be subluminal, and this sign is also related to having standard high energy completion. This is in the absence of gravity. Now I can start, if I want to, minimally coupling this field to gravity. So I'm going to include the Einstein-Hilbert term, and then all of those things include now interactions with gravity. I still have my light cone for my fluctuations on a non-trivial background being subluminal. I'm working here in the Einstein frame, and this is the light cone of light and is the light cone of gravitational waves. In the Einstein frame, gravitational waves just travel at the speed of light, which is the speed of light in the vacuum. But in principle, I could perform a field redefinition or a change of frame. I just change my metric so that I go into Jordan frame. So I have some non-trivial, non-minimal coupling for gravity itself, but in such a way that my scalar field phi here, I have lost its phi to the 4 interactions that I had. They're going to be pushed to higher order, but I'm just building my low energy effective field theory perturbatively. So this is all I have perturbatively to that order. Now in this new frame, and this is a trivial just frame transformation, it doesn't change any of the physics, it doesn't change anything at all, it doesn't change my notion of causality in any way. I put myself in this frame so that my scalar field phi here is just at this level is just entirely trivial, and it is it has an entirely luminal light cone. However, gravitational waves, because of those interactions, so the non-minimal interactions, I'm no longer in Einstein frame, will not travel at the same speed, will not travel at the speed of light in the vacuum, c being 1, and instead it'll travel, the causal structure will remain the same, so we'll have to travel faster than the fluctuations of phi, and will travel at what I will qualify as being superluminal. Of course, there's no violation of causality here because there was no violation of causality here. There's nothing interesting, particularly interesting happening with the fact that the gravitational waves seem to be traveling at a speed which I would qualify as being superluminal, is just because of the frame I'm working with. So in some low energy effective field theory, the fact that I want my field to be connected with what I would call something causal and enjoying a standard high energy completion would require them to be subluminal in the Einstein frame within the Jordan frame, imposes gravitational waves to be actually superluminal. This is the right sign for gravitational waves. So this is a trivial yet important frame artifact that we have to consider. And so really everything we're going to be talking about is not related to this possible superluminality, which is just a frame artifact. To the 0th order, we're just going to be imposing subluminality for all the fields once we have put ourselves in a frame where gravity can decouple. And in the Jordan frame here, what happens is, I should put it here, in this Einstein frame, I can smoothly take the limit where m Planck goes to infinity, and I know that because that's where I'm started with. However, the field transformation to go into the Jordan frame itself is singular in the limit where the Planck scale goes to infinity, and I shouldn't take the decoupling limit in this frame instead. Okay, so to 0th order, all of this makes perfect sense if I'm working in the frame where I can take a smooth limit where the Planck scale goes to infinity, and that in the original frame, by original frame here, I mean the Jordan frame now, this may imply some amount of superluminality for gravitational waves or possibly other fields. So this first trivial, entirely trivial, but still important remark is related to the fact that in a gravitational setup, if I'm not careful with the frame I'm working with and how I can take the decoupling limit, is not that just some species can be slightly superluminal, is that actually the right sign related with causality or with a standard UV completion for some of the species may simply be that those fields have to be entirely superluminal in a particular frame if I'm not working in the frame where I can smoothly take a decoupling limit and Planck goes to infinity. And then if I don't know any better, if I don't know how things scale as m Planck goes to infinity, a priori I cannot put any prior on whether some species have to be what I qualify as being superluminal or not. So this is, again, entirely trivial. We can deal with that if we know how things scale as m Planck goes to infinity. So for the rest of this talk, I'm always going to be working in an appropriate frame where I can go back to my feet and I can send the Planck scale going to infinity and recover a theory which entirely decouples from gravity. But if I weren't doing that, then I couldn't even start talking at all, and I should just end here. Okay, so with that in mind, let's go into the gravitational setup. Let me start with an effective field theory, let me start with a high energy theory. It may be full high energy completion. Probably it's just going to be a partial EV completion, depending on what you want. That includes gravity, it includes light and heavy modes. And below our energy scale m, I'm going to integrate out all the heavy modes that have a mass larger than m. This is all very symbolic. And here, just to say something, just to be concrete, I'm going to be considering the evolution of the tensor modes, so the gravitational waves, about a black hole solution. Okay, just to have a particular example in mind. Although none of what I'm going to be talking about will be so relevant, so much related to gravitational waves per se, and so directly related to that particular black hole configuration. So this is just an example. So I'm going to start with this is a partial UV completion because I still have gravity. I'm not dealing with, this is just the standard gravity and it's not string theory or whatever. I have my light modes and my heavy modes. I'm integrating out my heavy modes and I get all of these operators in my low energy effective field theory. I have, of course, a cosmological constant in my low energy effective field theory. And for lack of a better understanding of it, I'm just going to ignore it for now. So I'll set it to 0. Then I have all of my light fields. And for now, I'm going to consider the light fields to be minimally coupled to gravity. It doesn't need that all the light field be minimally coupled to gravity because I'm going to be working in the vacuum. So most of these contributions are not all going to disappear. All I want is that I have one field, let's call it the photon, just so I can say something, let's call it light, which sets up my standard light cone so I can start talking about something. So I just want one field which follows null geodesics as compared to the background metric so that I can set things up in respect to that particular field. Otherwise, again, I can just confuse myself in 100 type of different frame transformations. Since I'll be working in vacuum solutions, these are not going to contribute too much for now into the evolution equations and the background configurations. It's just a matter of setting up a relative light cone. Then the leading operators are coming into my low energy effective field theory in terms of the curvature operators are the R-square operators. If I'm working in 4D, and this is different in higher dimensions, but if I'm working in 4D, then those curvature square operator vanish in the vacuum. And so for Ricci flat black hole solutions in 4D, those operators are irrelevant. And the first operators which are relevant, well, they're more irrelevant, but the first operators which are become interesting for the configuration I'm thinking about are the curvature, the Weyl-cube operators. There's many of them, doesn't matter too much what they are. The only relevant one for Ricci flat black hole solutions are the Riemann or the Weyl-cube ones. And actually it happens that only one combination of those two operators is going to be relevant for the rest of this talk, which is that particular one. Okay, so everything is going to only depend on one particular coupling constant in which is a particular coupling constant related to the Weyl-cube or to the Riemann-cube operator in my low energy effective field theory. The sign of this coupling constant that comes in the Riemann-cube operator is determined with the precise field content of my partial or UV completion of the field that comes in above the cutoff of the low energy effective field theory I'm considering. And typically the sign of P is dominated by the spin of the lightest massive particle that I have integrated out. If it has been 0, 1, then this coefficient is positive. If it has been half, then the coefficient is negative. This you can see explicitly by performing the exact integration. Okay, so it can be both signs depending on the spin of typically the lightest massive particle that has been integrated out, because that's the one that becomes the most relevant in my low energy effective field theory. Okay, so this is the EFT I'll be working with. It's a purely gravitational EFT at this level. So I'm considering this, and the relevant parameter that is going to account for the perturbations of my EFT operator is this parameter here. On the background solution, it knows about the scale of the lightest field I have integrated out, the Planck scale, and RG is kind of the Schwarzschild radius of the black hole solution I'm considering. So this RG, you can take it just to be the Schwarzschild radius of the black hole that would happen just in GR without the presence of the EFT operator. because to leading order, this is just what it is. So in that particular EFT, I will have my solution, my metric for black hole solutions will be not exactly Schwarzschild, but something closely related to it with epsilon corrections. But on top of that, gravitational waves themselves don't see exactly this metric, because you need to account for the fact that this operator is present and affects the propagation of the gravitational waves themselves. And so as compared to other massless, other fields living on that space-time, gravitational waves, because of these operators, see a slightly different metric, which is corrected with this correction from the EFT operator. Okay, so this is the effective metric seen by gravitational waves in my low energy effective field theory. And this gamma here is the effective metric seen by species which are minimally coupled to gravity.
Sorry,
Yes.
Claudia, to interrupt
Yeah.
you. 10 minutes? It's okay?
Okay.
Sorry.
Okay, so let me go a bit quicker. So on that background, because the gravitational waves see a slightly different metric as compared to the other species, they will see a slightly different speed of sound, which is parameterized by this parameter epsilon here and depend on the Schwarzschild radius of the black hole you're considering. One thing you can notice is that at the Schwarzschild radius, at the photon Schwarzschild radius, this correction is 0, and therefore all the species share the same horizon. This is just a consistency relation. This is as it should be. But what's important is that whether or not gravitational waves are superluminal depend on the sign of this operator. And as we have seen before, this the sign of this coupling constant, this could be positive or negative depending on the precise field content you have beyond your low energy EFT. So in principle, from just staring at this sound speed, one might be inclined in setting consistency of a low energy effective field theory being related to subluminality of gravitational waves, and therefore this coefficient here being positive. But they are perfectly acceptable partial UV completions for my low energy EFT, where the next heavy particle is a spin half, for which the coupling constant will be negative, and therefore I'm led to slightly superluminal, or what I will qualify as superluminal sound speed for my gravitational waves on that background. Okay, there's no debating that at higher energy, the speed of gravitational waves will go back to 1. And we know that because this is where we got it from. We had just gravity coupled to heavy fields, and the only reason we have a departure from the speed being 1 is because we have included the operator from integrating out the heavy modes. Otherwise, we would go back to 1. So we know that. But the question we'd like to understand is, within the context of the low energy effective field theory, how come we could have what we qualify as a level of superluminal speed for gravitational waves and yet not be confronted with causality violation? Because in principle, as soon as you have the mildest level of superluminality, even at extremely low energy, you can consider a setup where you have, let's say, Minkowski here, you send up gravitational waves and you send up light. Then I have a lattice of black holes, or a blob or whatever you want in here, in such a way that gravitational waves send with arbitrarily low frequency travel superluminally. And then once you exit this lattice of black hole, you still have a significant support outside your light cone, which that you might be able to measure. So this is really the question we like to understand within the low energy effective field theory. Here we're just looking at one black hole configuration. So even though you can send, let's say, light or whatever massless particle, and you can set gravitational waves, if gravitational waves are traveling at what you think is a superluminal sound speed at low energy, you may observe a time advance for gravitational waves as compared to other massless particles. So we'd like to understand how this is consistent with the notion of causality. So very symbolically, the amount of deviation from luminality of gravitational waves is related to this parameter of my EFT and this coupling constant. And very symbolically, this is in an extreme scenario that will lead to a time advance or a time delay, which is this coupling constant time, the Schwarzschild radius of the configuration you're considering, so of this order of magnitude. And this in priori could be negative, so leading to a time advance if this coefficient there could be negative, which could be the case for some, what I'll consider consistent partial UV completion. So in order to understand how this is consistent with causality, really the key is to understand what is the level of time advance you can allow for yourself while remaining within the regime of validity of your low energy effective field theory. And so that means several things. First of all, it means that we neglected higher order curvature operators. So my low energy effective field theory is only under control so long as all of those operators are small compared to my cutoff, which is small compared to my Planck scale. And so that tells me that, of course, the Schwarzschild radius is large as compared to the Planck scale. I hope we agree on this. But more crucially for us, it's also a statement on the frequency or the asymptotic energy of the scattering wave or the scattering particle that I'm sending. So the waves have, I'm considering massless particle, they have no momentum. So there's no sense in considering contraction of K with itself. It doesn't give me anything. But any contraction of the full momentum of the waves we're sending with the Val tensor themselves have to be under control within my low energy effective field theory. And so it actually gives me a bound on the maximal asymptotic energy of the wave I have to send in for a particular cutoff of my low energy effective field theory. Or in other words, if I have a particular cutoff of my low energy effective field theory, I have to send in waves which have a sufficiently large wavelength as compared to the Schwarzschild radius of the black hole I'm considering. If this is not satisfied, then the wave I'm sending in, I cannot use my low energy effective field theory to determine its trajectory and to determine the time advance or delay that I will end up having in that particular configuration. So going back to the time advance or delay that we were accounting for in this configuration, we mentioned that we have this order of magnitude, but we also mentioned that we needed to have, of course, the Schwarzschild radius large enough, and we need to have this quantity bounded by the wavelength of the very particle, of the various wave that you're sending in, to be able to use the low energy effective field theory to predict its trajectory. And so that in practice means that the level or the amount of time advance or delay that you can account for within this configuration is bounded by the wavelength of the particle. So it means that ultimately the level of time advance, even if you could have a time advance in this configuration, can never be larger than the wavelength of the particle of the wave that you sent in. And so it doesn't make sense to be talking about a particle approximation in computing the trajectory of this particle if you're going to have some, if you're interested in corrections which are smaller than the very wavelength of the particle you're interested in. So in other words, the amount of time advance that you're having is not observable, is not resolvable. Is not resolvable neither within the high energy theory nor within the low energy effective field theory. Okay, so there's not really any support outside the light cone that you could really be talking about. This is not obvious from what I'm presenting in here, but ultimately what it means is that so long as you have a departure of your speed compared to luminality, which scales with the Planck scale by an amount larger than 2 or equal to 2, it will necessarily lead to time advance in this particular configuration, or a support outside the light cone within the low energy effective field theory, which is always going to be smaller than the wavelength of any wave you sent in, by requiring that you remain within the regime of validity of your low energy effective field theory. And this scaling of the speed is precisely the same as what we had for the approximate positivity bound we could allow ourselves in the gravitational setup for the coefficient in the coupling. Am I out of time now?
Yeah, of course. Go.
Yes. Okay.
Yeah.
Okay. So I'll stop here, and if you're interested in what I'm talking about. Otherwise, I'll
no,
go
sorry,
very
I
long.
misunderstood. So you can, yeah, you have 5 minutes more if you want.
Half a minute, okay.
Yeah, sorry.
Okay, so I'd like to make two small comments before I conclude, and I'm sorry for taking so much of your time. The first one is, if I like to be a little bit more precise in what I mean with the fact that the time advance we're computing is not being resolvable. It may seem that all I'm saying is that in order to be within the regime, it may seem that what I'm saying is that the amount of support outside the light cone that we will compute is above the cutoff of the low energy effective field theory. And this is not what I'm saying. If the amount of support you can outside the light cone that you would predict from this computation was above the cutoff, it would still be in tension with causality, because you could bring in an apparatus which itself live in the high energy completion of your theory that would be able to measure this support outside the light cone. So it's not about a time advance or delay being bounded by the cutoff of my low energy effective field theory. It's really important that the time advance is bounded by the very wavelength of the particle, of the wave that we're considering, so that it's really a failure of the geometric optic approximation. And if we wanted to resolve it, we would really need to account for the fact that what we're sending is a wave packet and not just a particle, okay? A second point I like to say is that a priori, all I'm saying here is that because it's so small, I can't really say anything, and so there may or may not be any violation of causality. I cannot talk any further, and it's true to zeroth order, but actually I can say a little bit more than that. Actually, it's not just that there's no link with causality. Is because the amount of support outside the light cone is so small, I can actually compute my retarded propagator perturbatively about the one I would have got without the EFT operator corrections. And by definition, if I do it perturbatively, I will recover precisely the same light cone structure than what I would have had in the absence of the EFT operators. So in compute, because the amount of the corrections I'm computing are so small, I can't do a perturbative approach, and then therefore by definition the retarded propagator, the retarded green function I'm going to compute will have no support outside the light cone. To be a little bit more concrete, if I have a wave of this form with a speed here which is not luminal, a priori we could always perform such an expansion. But the reason this is a dangerous thing to do in a typical scenario is because this affects the secular effects which grow in time. And this is related to the fact of the same thing as I was mentioning before. A priori, if you wait long enough, I can accumulate any mild level of subluminality to integrate them out to a macroscopic effect. So if these secular effects are large, this perturbative approach will break down, and I can't just compare the structure of this light cone with that light cone in here, or the retarded propagator I would get from here with the trivial one I would get from here. So this is in the standard scenario. But in this particular configuration where I argue that the any support outside the light cone is non-resolvable, we can actually do the perturbative approach, and what we have actually shown is that the secular effects are themselves bounded. They are bounded by some level of what corresponds to the wavelength itself. And therefore I can compute the retarded propagator, the retarded green function perturbatively, and if the zeroth order one, or the one I would have had without the EFT operator corrections, is zero outside the light cone, then I can act any operator perturbatively on this to compute the retarded green function for my EFT theory, and acting any operator on this one will still lead me to a retarded green function which is zero outside the light cone. And so I will have the same structure as what I would have had originally. And therefore there can be no violation of causality whatsoever. So it's not that because the level of time advance or time delay is sufficiently small that I cannot make a connection with causality. It's actually because it is so small, we are guaranteed that causality is preserved within the low energy effective field theory. Okay, a lot of the terminology I'm using here is with respect to the time advance or delay. But if you look at the literature, all of this is typically more done with the shift, and you can replace everything I've done here with the shift if you wanted to. So I'm not going to go through that right now. Okay, so let me just conclude. Now we all agree that the speed of gravitational waves is luminal to incredible accuracy. The level of the corrections I'm talking about here, I should have said, they're not anything we're going to observe in the next 1,000 years. It's not about comparing so much with, it's not about having a level of subluminality which is larger than this band in the first place. All of the EFT operators are extremely suppressed compared to anything that would be observable. It's more a matter of principle on whether we should segregate within low energy effective field theories against operators which could in principle lead to an extremely mild level of superluminality. So there's one just subtlety to be careful with. It's not really a subtlety, it's something everybody knows, of course. We need to be very careful in the frame in which we're working with, otherwise we're not really saying anything. And if we're not careful with that, actually the right connection with causality may sometimes be the requirement that gravitational wave may be superluminal by actually a large amount. This is just a small comment. More concretely, if we work in a frame where matter and gravity can decouple very smoothly, when the Planck scale is finite, we may have a small amount of superluminality or a small amount of time advance or a small amount of negative phase shift for gravitational waves or for other fields. And this does not need to be directly in conflict with causality. Actually, can be completely consistent with having a causal and Lorentz UV completion. In the frame where matter and gravity can decouple, what we can see is that superluminality can be consistent with causality so long as it is suppressed with the Planck scale, with sufficiently powers of the Planck scale, so that the amount of support you would otherwise have computed outside the light cone is not resolvable, or in other words, so that you can compute your retarded grain function perturbatively and you have the same support outside the light cone, the same absence of support outside the light cone as what you would have otherwise had the speed be exactly luminal. And then relating back to positivity bounds, or the presence of a small amount of negativity in the positive, what you would otherwise call positivity bounds. If you are dealing with a gravitational theory where you could have a T-channel pole, then the coefficient here does not need to be positive because of this contribution here. It just has to be positive when M Planck is infinite, but when M Planck is finite, it can be slightly negative by this amount. Okay, so I'll stop here and thank you for your time.
Thanks a lot, Claudia. Very nice talk. So, round for question. Is any question?
I have a question, Claudia.
Yeah.
Yes. So you're talking about this frame dependence. So do you see a general definition of this frame, in the sense that this choice would involve an infinite possible field redefinition? So what is the I mean, yes. I can understand what you mean in precise examples, but in general, what is the recipe to choose this
general example, I have to sit down and write it down precisely. The key thing is you can only make a concrete statement if you know how things are going to scale with the Planck scale.
Mm-hmm.
If you just have a low energy effective field theory with some coupling constant and you don't know what geometry combination this coupling constant is in terms of the Planck scale, if you don't know how it scales when you send the Planck scale to infinity, then, I mean, pragmatically, you can't really allow yourself to say anything, mm-hmm. because you don't know what is the right frame where gravity will decouple if you don't know how these things will scale as the Planck scale goes to infinity. Mm-hmm. So there's a little bit of a level where you need to commit of how this cascaded down from a partial UV completion before you can make any contact. I would say, honestly, if you don't know any better, if you don't know how things are going to ultimately scale with the Planck scale, you can't set any prior because you don't know what was the right requirement.
Mm-hmm. Yeah, okay, I understand. This was my question, but there is no.
I know exactly what you mean. I really have to sit down and work it out precisely, because this, I agree, this is an example where it's kind of trivial how these things work. But more generally, if you take the EFT of dark energy, I guess that's probably what we have in mind, we need to understand what in practice it means. What are the priors we have to put ourselves on the coefficient so that it's consistent with causality. All I can say right now is that I cannot give you a simple rule where everything, all the C's have to be subluminal. It's not going to be as simple as that.
Okay, thanks.
Sorry.
More question? Go ahead.
Yes, I have a question.
Oh, yes. Yeah, please go.
Okay.
I was mute. I was talking, but yeah.
Thank you. Yes, regarding this violation of positivity that you comment at the end, that you got it without assuming any explicit UV behavior. If I remember correctly from the paper, you get to this conjecture or to this assumption actually by exploring all possible renormalizable and non-renormalizable possible terms that you can add to the theory that you're exploring. So I mean, this is a bit like actually exploring different UV completions, right? So can you comment a bit on this?
This bound here. No, this is in the paper. We do explore various possibilities, and we always end up to that. But the reason we state this is not because we observed various situations and that was always the case. It's really more coming from here. We know that this has to be the case because we know the amount of superluminality we can allow for ourselves. And this is very clear. That's my fault. I haven't had the time to explain why that happens. But if you want, I can show it here, that you can see in that particular example, you're a bit too safe, right? You could have allowed yourself for a little bit more time advance, and you would still have a bound where this is smaller than that. So you actually have 2 powers of the Planck scales too much as compared to what you really needed to have. So that really tells you that when you're looking at the speed, you could have allowed yourself for even more. It didn't need to be so small. It could have been 2 powers of the Planck scale enhanced as compared to that. And so when you go back to the limiting case for your sound speed, so that you would still have a time advance which is bounded by the wavelength, that tells you that the limiting amount is just suppressed by 2 powers of the Planck scale. So this is not clear because I haven't explained it, but you can see, you can work this out more precisely. And then the fact that this thing has to go like 2 powers of the Planck scale, then that you can see directly relates with this quantity having to go with 2 powers of the Planck scale. So we see that in the examples that we show in the paper, exploring various types of non-renormalization theorem. Actually, we have something else coming up where we don't need to explore any configuration. We can just put a bound on the cutoff straight away. But I don't want to talk about that before we have it out. However, we can see that this is the generic rule. But not assuming any specific UV behavior, what I mean is that you don't need to commit to a particular amount of violation of the Froissart bound, for instance, or any particular way your UV completion is going to be realized, for instance, as a tree-level, weak coupling, high spin completion, or anything like that. So that may happen, in which case you can have a stronger bound here, and that has been explored. There are very interesting things being explored there, but I'm not necessarily committing to any particular such level of realization.
Okay, thanks.
Claudia, can I ask, can you comment a bit on the relation between your result and the one of the paper by Camagno, Eidelstein, Maldacena, and Gibaedov?
Yes, yes. So, okay, so what they have shown, so they do it not for this EFT, right? But you can transfer all of that. So they're with respect to this particular context, what they claim is that it's okay for you to have, maybe I should write it down. So when you're in your low energy effective field theory, you will have already from the trajectory of other massless particle, they will see a time delay as compared to what would have happened had you just been on Minkowski. This time delay is just due to the fact that you are in a particular black hole configuration here. And then on top of that, the gravitational waves in this context have an additional correction which I indicate as delta TEF. So that this EFT time delay is relative to the other massless species present in a spacetime, but still on the background of the black hole. So in the paper you mentioned, their resolution is saying it's okay for this quantity to be negative. So to have a time advance of, in this case, it would be gravitational waves. They haven't done it for that, but it would be gravitational waves as compared to normal species, so long as normal species have a sufficient high time delay so that the overall time delay of this one plus the time advance of that one compared to this one leads to an overall time delay. So the time delay of the blue one plus a negative contribution here is still a positive contribution. So that is their claim. But this is not sufficient, because it's so long as you have this possibility of setting up a configuration where you can have a time advance as compared to light, then you can use this to your advantage a priori. If I don't say by which amount, and so if you could allow yourself to have a large comparison here, so long as you compensate by large positive contribution here, you could still set up configurations where you send some signal that then would travel faster than light, and then you would have some support outside the light cone set up by light. And that is something we would consider as a violation of causality.
Well, can I make an analogy to be sure that we are, so if I have a light, sorry, this is a trivial analogy just to be sure. So light in the vacuum has a speed of light, then there is an index of refraction in a medium, it slows down.
Yeah.
And then you want to avoid the possibility that some other fluctuation that has on vacuum has either the same or less speed than light.
Yeah.
In the vacuum, in the medium, has to slow down always more than light.
Yeah.
So even if both of them are, they are slower than the speed of light on the vacuum, no? So this is what you are saying. But don't you believe that in order to see actual violation of causality, you have to build in if you can really make some sort of a Gedanken experiment in which this applies? Because at the end you are in fact.
Yeah, I can respond to that exactly. The problem here is slightly different to what you have in mind, in that this thing here being negative is negative compared to the gravitational waves time advance you would have had for infinite or very large gravitational waves frequency. So this is the issue. I mean, when you think of sending light through a medium, it's only traveling slower than what you would otherwise think the speed of light is. It's only traveling slower than the speed of light at low frequency, but at very high frequency, it's still traveling at the speed of at the speed 1, let's say. Here the issue is that it's traveling at a speed which is faster as compared to the high frequency speed. And so as soon as you do that, if you could do that at wish, even by an infinitesimal amount, if you could do that at wish, you integrate that out, and you have low frequency modes that travel faster than the high frequency modes. And so you can set up an experiment where you integrate those out, and you end up with an amount of advance which is macroscopic. So the key thing is whether the amount of time advance really is macroscopic in this picture. But if this thing is not bounded by length, if it was just bounded by the cutoff, for instance, that would be an issue, because I could send in low frequency gravitational waves modes, and then I would have a time advance as compared to the high frequency gravitational waves mode. Even if it was smaller than the cutoff of my low energy effective field theory, nothing demands that I then measure this time advance with an apparatus which is a very high energy. And I'm comparing a situation where I go from Minkowski at infinity to Minkowski at infinity, let's say. So
let me say the stupid point. So are you saying that the high frequency modes are like saying on the vacuum, so to say? I mean, they are unaffected?
Infinite frequency mode, yes, infinite frequency modes are always like in the vacuum. They're always unaffected.
Then, I mean, sorry, maybe I missed something. We said that the Camagno et al. Paper was claiming that with respect to the absence of matter of anything, you can't be superluminal, so to say. So the total delay time has to be, you can't have an advance, no?
In the absence of matter, yeah, that's always the case. Yeah. I mean, in the absence of any spontaneous breaking, there's nothing, yes. But they say a little bit more than that. They say that the time advance compared to, let me say, normal species is not sufficient to overturn the time delay that other species have as compared to Minkowski, which is true in this particular context, but is not sufficient to prove causality.
When you mean causality, you talk about closed time-like curves? I mean, I'm not sure I understand what you're worried about. I mean, because having a broader light.
Let me say what I mean by causality is whether you could have, let me see. Typically, we make contact with causality when we say that you could have some support outside the light cone. Yeah, just having. I would as a causality violation any situation. I'm conservative. I would class as causality.
But it's not enough. Broadening the light cone is not enough to create, for example, a closed time-like curves, because it's still stably causal, the metric, right? So you need really to tilt the light cones in such a way that they are. You basically allow to go back in time. You mean if you have a metric which is just disformal to another metric, that is not enough to get causality violation.
We're going here into the type of argumentation we could go if we still had an issue, but we don't even have that issue. So what I will class right now as causality violation, and I'm being conservative here, is any situation where I can start with Minkowski or something asymptotically flat from somewhere, end up with somewhere when I'm asymptotically flat, and have a support outside the light cone of infinite frequency modes, which is measurable.
But that isn't, for example, what happens in the Charnost effect. You have the parallel plates of the Casimir effect, and you can compute that you have a low energy effective Lagrangian, which is the Euler-Heisenberg Lagrangian. Due to the effective Lorentz breaking present by low energy by the parallel plates, you have that the light propagating between the two plates orthogonally is faster than it would do parallelly. But at high frequency, exactly as you say, you go beyond the plasma frequency, you don't see the parallel plates. So the light in the UV, basically you recover the standard causality. In the infrared, you have broader light cones. And that is something that in principle has never been measured. It can be calculated, but in principle you can create it, because basically you have the metric felt by light parallel to the light cone, orthogonal to the parallel plates is basically the original metric plus a contribution, which is the vacuum polarization between the plates. So that is basically opening the light cones by a point. So I don't see, in a sense that this seems a very mild situation. It's not really a big issue, no? It's a big problem for causality. We know that we cannot do by a time machine with that.
No, I mean, not,
I'm worried. I wanted to make
not everybody would agree with you.
Okay.
Not
I have a question for you.
Sorry, but as soon as you're in that configuration, it's not like I'm gonna write down a way to build a time machine out of this, but in principle you can think of then performing a boost here where and comparing with the boost there, and then you have well, let's just do a boost in here now. Here you're just in Minkowski, let's say, and because this is you ended up with a support here which was larger. Well, you have a distance in here, right? So
no, but that is like the touch and telephone, anti-telephone, what you have in mind, probably. You mean that when you have a superluminal signal, you can in principle close the time loop. But
yes.
When you have this formal metric, you can show that it doesn't work. There is, for example, a paper which is a complement by a paper to Barattaz et al., by Mukhanov and other people. I can't remember now all the name, but they are really dealing with the kind of this formal metric you get in this theory, showing that for this kind of causality in the sense of closed time curves, as long as you don't tilt the cones, but you just broaden the cone, then you are in a safe, because basically they are all stable causal. They all admit a global time likely inverter at the end of the day. So you cannot really invert the sign of time. But the question, I think, what is the, okay. I'm not sure
if I agree with this, because here you have Minkowski, here you have Minkowski, and you shouldn't commit to a particular direction of time. So as soon as you broaden your light cone, you can perform a boost, and there's no notion of time, preferred time, neither here or there. Of course, there has been something specific happening in between, but once you have set that up as an experiment, it's very different than in the cosmological setup, even here, where you can set up your preferred time direction. In here, you are abstracting yourself asymptotically from any preferred direction. And so as soon as you have a little bit of a tilt of your light cone, it doesn't need to have been all the way flat, but as soon as you do that, then you perform your boost and you get into a light cone where
you can go in a frame. You can go in a frame where the luminal particle is the causal particle is the one with a broader cone, and then you can see that it's like anyway. There is literature about this that this kind of things when you have this formal metric do not work. But I think that there is another point that you made, and I would like just to ask you about the Schwarzschild geometry. If you have in a Schwarzschild geometry a different light cone for graviton and photons, does it mean that you have different horizons for them?
No, it doesn't. That's the beauty. You can see.
It doesn't. Okay. Then it's okay.
So look at here. See, the horizon is exactly the same. The correction to the speed.
Sorry, I missed that point. Okay. Sorry.
Yeah.
Okay.
Yeah. So yeah.
Which is good. Otherwise, that would have been a serious problem. Okay.
That's right. But you can show that if you're ever in a situation where they don't share the same horizon, then your EFT wouldn't have been under control anyways, because then you can compute invariants which are singular at the various not agreeing horizons, right? So because you're working in this EFT context, it has to be the case that everybody shares the same horizon.
Okay, thank you.
Yeah, but I can say that as a party line. It's not it's not obvious to see. Yeah.
Okay, I think we can stop here, or if you want another question, but we are 1 hour and a half. So
sorry for running.
No,
Your time.
pretty good. So thanks again, Claudia. Very nice talk.